This is the demonstration for paper 9.3, a 60 GHz CMOS phased array transceiver pair for multi-gigabit per second wireless communications, presented by Cybeam from Sunnyvale, California. So this demonstration showcases the Cybeam RF transceiver pair in a wireless HD system. Shown here is our simplified transceiver architecture. You see that the two RF chips use the same circuit blocks, but the RF paths are designed to create an asymmetric link capable of 3.8 gigabits per second for full HD video in one direction and 10 megabits per second omnidirectional link for control and coordination in the reverse direction, at the same time maintaining quality of service required for a video application. Since both chips are transceivers, we distinguish them as the source and sink chips based on the high and low data rate directions. When the source is transmitting to the sink, we'll have 32 of these TX elements connected to 32 RX elements on the sink side. And then for the reverse direction, when the sink is transmitting to the source, we'll have 8 of these TX elements transmitting to 4 of these RX elements. An RF element is consisting only of this phase shifter and either a PA or an LNA, and then an antenna, which is integrated in the package. We use a single path up to the end of the mixer or the beginning of the mixer, and then use a binary tree for distribution out to the 32 elements. By having multiple RF elements, in-air combining improves the transmitter power and efficiency and the receiver sensitivity. In addition, the phase shifters and antenna array can electronically steer the beam to find a path with sufficient link margin in case an object blocks the current path. So the setup we have here for our demo includes our internal engineering modules. What we have here is the source module, which is connected to a PlayStation 3, and then we have a sync module, which is connected to a 3D TV. So this is an example of the source module, and you see here we have our package, the top side of our package with our antenna array showing 40 integrated antennas in the package, 32 of which are used for the high rate PHY data, and then either 8 or 4 are used for the low rate reverse channel. Also included on this board is our baseband chip for this wireless HD application. We also have another source in this network, which is an integrated source module, which is inside this Alienware laptop from Dell. We actually have a split board design here, where we have the baseband chip is now on a separate board and then connected for power and for data over to the RF chip, which is on a smaller board, so that it can be placed inside the lid of this laptop to try and maintain a good line of sight link. And right now you can see that the TV and the laptop have a 3 gigabits per second link showing full HD video, and this is acting in an extended display monitor mode. So you can see that we have some video shown here on the laptop screen, and that's also showing up without any lag on the TV itself, and then we have just a trailer looping over on the TV. Also part of our demo, we show what we call beam display, which is some internal MATLAB code that we have running on this laptop, which is connected to the sync module with a USB cable. And over the USB control, what we're doing is we're reading out all the phase shifter settings on both the sync and the source side, and then calculating in real time what the beam pattern looks like. So these beam patterns are updating and are limited by the MATLAB software code, and they actually run much faster in the chip itself. What these plots show are on the top 3, these are for the source side, and those bottom 3 are for the sync side. And this is azimuth angle, this is elevation angle, and this is a 2D combination of both as a heat map. And what this allows us to see is that, for example, on the source side, if I take this Alienware laptop and I pick it up, from the point of view of the TX element, now it needs to look down to see the source, to see the sync side of the link. And then also if I rotate the laptop around, you see the azimuth changing. And it's basically trying to find the best possible link in order to maintain the 3 gigabits per second of full HD video. Well, that's it for this demo. Thanks for your attention. And if you would like to see any more details, please see our paper 9.3.